In Lesson 5, we talked about polynomial identities, and these are statements or equations that are always true. Regardless of what numbers you substitute in for the variables, both sides will always equal each other. It's a true statement. And we proved that some of these were true by applying these operations, by adding, subtracting, multiplying, and dividing these polynomials together to showing, look, I can take this one side and make it look like the other. So, number 1 says, prove that x plus y squared minus x minus y squared equals 4xy for all real numbers x and y. So what this means is, if you picked your favorite x and your favorite y, plugged it in on the left side, plugged it on the right side, they'd always be the same. So how do we prove this? Well, whenever we prove a polynomial identity, we start with one side, apply algebraic manipulations to it, make it look like the other side. So I'm going to start with this left-hand side here because it looks like there's a lot I can do with it. So I'm going to start with x plus y squared minus x minus y squared. I'm going to start with that and hopefully end up here. This is where I want to end at. Notice that I didn't write 4xy here. That's going to be all the way at the bottom here after I apply some algebraic manipulations. So I have to square x plus y. So if I square x plus y, what do I get? X plus y, x plus y. I get x squared, xy, xy, and y squared. So that gives me x squared plus 2xy plus y squared. That's what that first guy is. Minus the second thing. Well, in this lesson, we kind of learned how we could square things quickly without making a table, and I'm going to use that right now. Square the first, multiply them together, so x times negative y times, then we stick a 2 in front of that. So minus 2xy, and then square the last, plus y squared. That's a quick way of doing the table whenever you square things. That's what we talked about in this lesson. That's an identity we proved in this lesson. Okay, somehow this magically has to become 4xy. Let's see how that happens. Well, I'm going to distribute that negative 1 that's sitting in front of that. So minus x squared plus 2xy minus y squared. Well, x squared minus x squared, those add to 0. Y squared minus y squared adds to 0. 2xy plus 2xy gives me 4xy. That is my proof. I started with one side, made it look like the other side. I didn't work with both sides of the equation. I didn't just keep writing the same thing and manipulating them. I started with one side, made it look like the other. So we proved that if you picked any x and y, plug them in, you really just be doing 4 times x times y. Prove that m plus n cubed equals that expression is an identity. So prove that m plus n cubed gives you that. So I'm going to start with this side, show it looks like that side. M plus n cubed. Well, what does it mean to cube something? That means I have 3 of them. Right? Well, I can't multiply 3 things together at once, so I'm going to start with those first 2. Well, that's m plus n times m plus n. I'm squaring that. So square the first, 2 times their product, plus the last thing squared. You could have made a table for that as well. Multiply those first 2 together. You get m squared plus 2mn plus n squared. You could have made a table on the side and multiplied them together and gotten that same thing. Times m plus n. Fix that up there. So if I was to make a table on the side here, let's see, m squared plus 2mn plus n squared, mn. Okay, so it's a 3 by 2 table here. M squared times n is m cubed. 2mn times n is m. Sorry, 2, well, I have m squared, didn't change the n. N squared m. All right, now distribute the n in. M squared n. He gets another n, so that's now n squared. That's n cubed. So when I multiply those together, I get m cubed plus Well, those m squared n's are like terms. So I have 2 plus 1 gives me 3 m squared n. If these guys are actually like terms here, if I use the commutative property, mn squared, so I have 3 of those as well, 3mn squared plus n cubed. So we prove that this is an identity. If I want to cube a binomial, if I want to cube something plus something else, this is what my answer is going to be. Now, would I memorize this like I would the squaring one? Probably not. I would just do it out. But it is an identity. It's always true. Before we move on, I want to note that I started with one side, made it look like the other. I started with the left-hand side, made it look like the right-hand side. The identity x squared plus y squared squared equals x squared minus y squared squared plus 2xy squared can be used to generate Pythagorean triples. Show that this statement is an identity. So I can actually work with both sides here, but notice how I'm going to do this. I need to show that they're actually the same thing on both sides, that both expressions on both sides are actually equivalent. So I'm going to start with x squared plus y squared squared. See what I get. Well, what does that give me? When I square something, that means multiply it by itself, doesn't it? So I can make a table to help me out here, or you could use the squaring identity that we proved in class. It is very helpful. X squared times x squared is x to the fourth. That's just x squared y squared. That's also x squared y squared, and that's y to the fourth. So that gives me x to the fourth plus, I have 2 of those x squared y squared terms, plus y to the fourth. Now if I take the other side here, I'll do that in blue. There's nothing else I could really do there. So now I'm going to kind of start over here at the blue. I'm going to start with x squared minus y squared plus 2xy squared. What does that equal? Forgot a square there. Well, I'm going to square that binomial quickly. Square the first, 2 times their product, square the last. Plus, well, how do I square 2xy? Well, that's 2xy times 2xy, which gives me 4x squared y squared. Okay. Combine like terms. I have x to the fourth minus 2x squared y squared plus 4x squared y squared gives me 2x squared y squared plus y to the fourth. Well, wait a minute. These two things are actually the same. So we've proven that this identity is true. We've shown that x squared plus y squared squared equals x to the fourth plus 2x squared y squared plus y to the fourth, which equals x to the x squared minus y squared squared plus 2xy squared. So I know this looks complicated, but all you're doing is a bunch of algebraic manipulations. To prove that this is an identity, I notice how I worked with each side separately and said, wait a minute, they're actually the same. So you can't just work with one side, and we can't work with both sides in the same equation. You can't say I have stuff here and work your way down both ways doing algebra. That's bad. You have to work with one piece at a time. Work with one side of the equation at a time. Pick values for x and y where x is bigger than y to generate a Pythagorean triple. Well, this is kind of like a squared plus b squared equals c squared. So let's pick values for x and y to get a Pythagorean triple. So let me just rewrite that identity on this page. Equals x squared minus y squared squared plus 2xy squared. So I need to pick any x and y where x is bigger than y. So maybe let's do 3 and 1. Why not? Let's see what identity we get here. So 3 squared plus 1 squared equals 3 squared minus 1 squared squared plus 2 times 3 times 1 squared. 9 plus 1 is 10 squared equals 9 minus 1 is 8 squared plus 6 squared. So what Pythagorean triple did I generate from this? I generated the 6, 8, 10 Pythagorean triple. Pretty neat. Pretty neat that I can make Pythagorean triples by using this identity here. It doesn't matter what x and y you pick. Whatever you plug in there, that 10, 8, and 6 are going to be your side lengths, because this is really a squared plus b squared equals c squared. So that inside, that's your Pythagorean, those are your sides of your right triangle.